Hello everyone. Welcome to this one short video on the fifth unit of electronics engineering, that is communication, which has been made keeping in mind that this video may help you in exams as all the important concepts of communication are covered in a single video. So let's get started. First of all, we should know what is communication. See, communication, as we all know, it is very simple transfer of information between transmitter and receiver or from one place to another. But in electronics, the most important thing that you must include in the definition of communication is through a communication channel or via a communication channel. That means communication is the transfer of information from transmitter to receiver through a communication channel, and this channel could be either wired or wireless. Now comes what is telecommunication. Telecommunication, whenever this term comes in front of us, we should always keep in our mind that telecommunication means that the distances involved in this communication are long. Alright, so whenever the communication takes place over long distances, it is called telecommunication. Now comes elements of communication system. Very important question from the point of view of exams as well. Comes many a times either in 2 marks or in 5 marks. If it comes in 2 marks, you can draw only the diagram, but if it comes in 5 marks, then you must explain each and every block as well. Now, first of all, when we talk about elements of communication system, just we should think that what are those important elements without which communication is not possible. So from the definition, we can easily reach the inference point that transmitter, receiver and communication channel are the most important ones. But besides these blocks, there are other blocks also. Which are they? They are input transducer, output transducer and noise as well. See, what is input transducer? For example, your information is in the form of speech, or it is in the form of text, or in the form of music. So we cannot transmit the information as it is, or we cannot give this information as it is to the transmitter, because every type of block is able to process a signal in a particular form. So therefore this information, in whatever form it has to be converted from its original form to an electrical form so that it can be further transmitted. Alright, so what is the function of input transducer? Input transducer converts the original information from its original form to the electrical form. Very simple. Alright, then further this electrical form is fed to the transmitter part. Transmitter performs several functions like amplification. Most important one is modulation. Alright, so amplification and modulation are the most important functions which a transmitter performs. Now, this information further goes on the channel. On channel, it is very much sure that some type of noise will be for sure added to this particular signal. So noise is also an important part in the communication system which has to be taken care of. Alright. Now this noise, I have shown this noise here. Now this signal further goes to the receiver part. What does the receiver do? Receiver further performs demodulation, that means the opposite of transmitter. Transmitter performs modulation, therefore the receiver has to perform demodulation. It again performs the amplification and it also filters out the noise that was introduced on the channel. Now the receiver has demodulated the signal. Now this signal, which is in the electrical form, reaches the output transducer and output transducer converts it back to the original form. So this is how communication takes place. That means if you have sent a music signal, it will reach the receiver in the form of music signal only. So which part is going to convert the signal into the original form, that is the music part? This output transducer. Alright. So these are the elements of communication system. Now the next topic towards which we will move is baseband signal and baseband transmission. I have told you during explanation of elements of communication system that transmitter performs modulation, alright, but it is not always necessary that the signal has to be modulated. Sometimes the signal is even sent without modulation, alright. Sometimes it might be possible that modulation is not required. So whenever a signal is sent without modulation, that means whenever the signal is sent as it is, that means as it is means if the signal is, if your information is in the form of music or in the form of text, it will be converted into electrical form for sure by the input transducer, but it might be possible that the transmitter does not perform modulation or does not find it necessary that the modulation has to be done. So that signal, that means the signal in its electrical form, or you can say the electrical equivalent of original information, that is called baseband signal, and its transmission is called baseband transmission. So I hope I am clear. So whenever the signal will be first of all converted into the electrical form, and if this electrical equivalent is sent as it is without any modulation, so this signal is called baseband signal, and the transmission of the signal is called baseband transmission. Alright. Now comes modulation, which is very important, and it is for sure that it will come in the exams. Modulation. Now what is modulation? See, what is modulation? In modulation, first of all, you will be having two signals. One is your message signal and the other will be a high frequency carrier wave. Alright. When you mix both of these signals, some parameters of your high frequency carrier wave will be varied or it will be changed, and they will be changed according to the message signal. I have explained it very well in my video for modulation. So I have given the links of all the topics in my description box. If you want to refer to any specific topic in a detailed manner, you can go to that particular link and you can go through that video. Alright. So modulation is, what is modulation? In modulation, basically we have two signals. One is our message signal and the other is a high frequency carrier wave. So when we mix both of these signals, very important thing to be kept in mind is the parameters of high frequency carrier wave are going to be changed. Your message signal is not going to be changed in any respect. If you will change your message signal, or if your message signal will change, then what will happen? The function, or you can say the objective of your communication will fail, because you are altering your message signal which is to be sent from the transmitter to the receiver. So it has not to be varied in any respect. In fact, when you will mix these signals, you are going to change the parameters of high frequency carrier wave, and these parameters can be amplitude, frequency or phase. Alright, so this process is called modulation, and if you are going to vary the amplitude of the carrier wave, will be amplitude modulation. If you will change the frequency of carrier wave, it will be frequency modulation, or if you are going to change the phase of the carrier wave, it will be phase modulation. So this is how various types of modulations are defined. Alright, so the same thing I have shown in the diagram as well, where we have a modulator block, we have a modulating signal and a high frequency carrier wave being fed into it, and finally we are getting a modulated signal. Alright, now let's move forwards for the needs of modulation. Again, a very important topic, that why is modulation required? Question sometimes comes under the title, why is modulation required, or simply what are the needs of modulation. So you have to mention all these needs. So the first important need is to reduce the antenna height. How the antenna height is reduced? Simply you have to remember that the minimum height of the antenna required to transmit any signal is h is equal to lambda by 4, where we all know lambda is the wavelength. Alright. Now we also know that c is equal to lambda f. So from here we get the formula as c by 4f. Alright. Now if we take in the case of modulation, because you are mixing a message signal along with the high frequency carrier wave, so basically that whole mixture will be a high frequency signal, because you have mixed your message, or you can say you have hidden your message into a capsule of high frequency carrier wave. Now your message is inside a high frequency carrier wave. This is your message and this is your carrier. You have hidden your message inside a high frequency carrier wave. Now this capsule is visible, alright? This capsule is being transmitted on the channel. Now this capsule is high frequency. That means this mixed or modulated signal is high frequency. Why it is called modulated? Because you have made your message signal to sit inside the carrier wave. So overall the signal is hidden, that the capsule is formed of high frequency. Alright. So let's take in the modulation, let's take a case 1 where frequency is low, and the frequency low means that is message signal, because your message signal was having a low frequency. Alright. This is message signal with a small circle, and it is having a very low frequency. Alright. Therefore we need to hide it inside a capsule of high frequency so that it can get transmitted over the channel. Otherwise its power will be lost and the signal will be lost if you will transmit it as it is. So the message signal has a low frequency. So we are going to take here two cases, one with low frequency and one with a higher frequency. So one frequency is 10 kilohertz and the other frequency is 1 megahertz. So when you will find out the height in both the cases by the above formula, you will get over here h equals to 7.5 kilometer, and here you will get h equals to 75 meter. Alright. So we all know for the first case, an antenna of height 7.5 kilometer is not possible to be installed, and an antenna of height 75 meters is quite possible to be installed. Therefore, in order to reduce the antenna height as well, we need to do the modulation. The next need is to avoid mixing of signals. See, there are many cases where the transmitters are multiple, but the signal which has to be transmitted by them have the same frequencies. Alright, as you can see, signal 1, signal 2, signal 3, there are multiple transmitters to transmit these signals, but all these signals have the same frequency which are to be sent to the same receiver. Now, if all these signals are sent to the same receiver, then the receiver will not be able to distinguish which signal has come from which transmitter if you are going to send these signals without any modulation. So in order to avoid this mixing, what we need to do is we are going to modulate them with the carriers of different frequencies. One we have, as you can see, I have taken 300 kilohertz carrier, I have taken 200, and I have taken 100 kilohertz carrier. So when you will mix them with different carriers, their products will be of course different. Alright, so they will obviously they are going to occupy different frequencies on the channel, and hence they will not be mixed. So that is why also modulation is performed. Next is to enable multiplexing. Multiplexing is same. Multiplexing means means many. When many transmitters are transmitting simultaneously on the same channel. So there are three things to be kept in mind. Many transmitters on the same channel simultaneously. Alright. So that means when multiple transmitters are transmitting on the same channel simultaneously, then in order to avoid mixing, modulation is done, as you can see on the above part. Next, obviously, it is going to increase the range of communication, because when you will make your message signal to hide in a capsule of high frequency carrier signal, then that high frequency capsule is obviously going to have much more power, and it will be easily going to get transmitted, or it can travel a longer range. So the range of communication can be increased through modulation. And modulation also improves the quality of reception, because the noise does not affects or barely minimum affects your modulated signal. That means the quality of reception will increase. So these are the needs of modulation. Now comes what are the types of modulation systems. See, based on your message signal, meaning that your message signal can be either analog or it can be digital. So if the message signal is analog, then it is analog modulation. If your message signal is in the form of digital, it will be or in the form of pulses, it will be a digital modulation. So analog modulation, just you can pay attention to the tree diagram only, because in our syllabus for the first year we only have amplitude modulation. Alright, so we just need to know the names. So one is analog and digital. Analog is further classified into amplitude, frequency and phase, but frequency and phase are collectively included in angle modulation. Alright, and then pulse modulation. Digital modulation is further classified into pulse code modulation, then differential pulse code modulation, delta modulation, adaptive delta modulation. Or so this is the digital modulation types. You just need to remember this tree diagram. You must be well aware with the names. But in our syllabus of first year electronics engineering, only amplitude modulation is included. Otherwise, we have a separate subject for this particular all the communications or modulation systems or strategies, that is communications in AC branch. Now let's move to the amplitude modulation. Amplitude modulation, as I have already told you during the definition of modulation, that when you will change the amplitude of carrier wave according to the message signal, it will be amplitude modulation. So you need to pay attention to certain terms over here. Instantaneous word is very important. Instantaneous means at that particular time, whatever will be the value of your message signal or modulating signal, the carrier will change according to that value. So you are going to vary the amplitude of high frequency carrier signal according to the message signal, but the important term is according to the instantaneous value of message signal or modulating signal. So this is the waveform. As you can see, I have taken a low frequency message signal, and this is how we represent the message signal, and a high frequency carrier wave. Alright. Now we have to mix them up and we will get an amplitude modulated signal. So how to draw an amplitude modulated signal? As we have learnt in the concept above, that in the case of amplitude modulation, the amplitude of this carrier will change according to the message. So first of all, let's draw an envelope or an outline. See, just pay attention to your message signal above, and I will draw the envelope according to it. Same as that of message signal, but from here the envelope will go like this, and similar envelope will be drawn like this. So this is the outline, but you are, in the case of amplitude modulation, you are only going to change the amplitude of carrier, not its frequency. So the carrier frequency will remain the same, and as you can see here, the amplitude is changing according to the message signal. So only the amplitude has changed, but the frequency remained the same. Alright, so this is how we draw the amplitude modulated wave. Now let's move on to the mathematical representation of AM wave. Very important. and let's see it. This is very interesting. So let's derive the expression for amplitude modulated wave. So let's see how it is derived. First of all, we will take a message signal. As you can see above also, I have taken the message signal as a sinusoidal signal. And the general representation of a sinusoidal signal is A sin theta. Alright. But here for convenience or for derivation purpose, we are going to take the another form of sinusoidal signal, that is cos theta, A cos theta, because both sin theta and cos theta comes under the category of sinusoidal signals. So here we are going to take, instead of A sin theta, A cos theta, and instead of A, I am going to represent the amplitude of the signal by Em, where E, capital E, and M represents the message signal, cos omega mt. A cos theta or A cos omega t, so similar is Em cos omega t. Omega is the frequency or angular frequency of message signal, where the subscript M stands for message signal. Same is the case of carrier signal, Ec cos omega ct. Now let's write down the expression for the amplitude modulated signal. Concept is the amplitude of carrier will change. So what was the amplitude of older carrier, original carrier? Ec, it is changed now. So let it be a new amplitude has come here, alright, but the frequency remains the same. So everything else will remain the same, only the amplitude has changed. Now what is the new amplitude? It is the older amplitude which has changed according to the message signal. So full message signal. Alright. Now let's open the terms. And let's take EC common. So it will be left like this. Now this ratio is very important, and it is represented by small m, which is modulation index. Very, very important. Alright. Now let's replace it with EC 1 plus m cos omega mt. This is only A. We were only calculating A, but our aim is to calculate the full expression of amplitude modulated signal. So A cos omega ct, let's replace the values. EC 1 plus m cos omega mt into cos omega ct. Alright. So when you will open this bracket, alright, let's open this bracket. It will be EC cos omega ct plus m cos omega ct cos omega mt. Now let's separate this trigonometric identity by the expression 2 cos A cos B equals to cos A plus B plus cos A minus B. So we will have EC cos omega ct plus I left EC over here, MEC by 2 into 2 cos omega ct cos omega mt, and I am opening it here as cos A plus B plus cos A minus B. So we will be left with cos of omega c plus omega m into t plus cos of omega c minus omega m into t. So this is the expression of amplitude modulated signal. Very, very important, which we all must remember. So when you will open these brackets further, you will get MEC by 2 multiplied with both the terms. Now if I look, so in total, how many terms we have in the amplitude modulated signal? We have 3 terms. First one is the carrier signal. Another one where the frequencies are getting added, it is USB, that is the upper side band. And wherever the frequencies are getting subtracted, it is the lower side band. Alright. Now what is the amplitude of carrier? If If it is in the form of A cos theta, so A is the amplitude. So here EC is the amplitude and the unit of amplitude is volts. What is the frequency of carrier? If we talk about omega c, it is the angular frequency. So omega c by 2 pi represented as Fc, frequency of carrier, and of course it will be in hertz. Amplitude of message signal. Message signal was taken here as this one. So EM and the frequency of message signal is omega m by 2 pi. So EM, again the unit will be volts. Frequency represented by FM, omega m by 2 pi, unit will be hertz. Amplitude of upper sideband and lower sideband. When you will open the brackets over here, you will see that MEC gets multiplied by both these terms. So MEC by 2 will be the amplitude. Unit is volts. Frequency of upper sideband is Fc plus Fm, or you can write omega c by plus omega m by 2 pi, which is same as Fc plus Fm. And frequency of lower sideband will be given by Fc minus Fm. Units are hertz. So these are the important terms in an amplitude modulated signal. First of all, you should keep in mind that it consists of three terms: carrier, upper sideband and lower sideband, and you must know how to represent the amplitude and frequencies of all the components individually. Now let's move forward. Another point comes is the frequency spectrum of AM wave. So frequency spectrum is nothing but the graph of frequency and amplitude, with amplitude on y-axis, and as we have seen above, the unit of amplitude is volts, and frequency on x-axis with the unit hertz. If you are asked to draw the frequency spectrum of AM wave, you must know that it has three terms: carrier, upper sideband and lower sideband. So the carrier frequency is Fc. Let's mark it. Upper sideband has frequency Fc plus Fm, so obviously it will be on right to Fc, and lower sideband Fc minus Fm. Now amplitude, if we see that the amplitude of carrier is EC, you can see upwards. Fc plus Fm and Fc minus Fm both have same amplitude, that is MEC by 2. Whenever you will calculate it numerically, you will always find that these amplitudes are lower as compared to EC. So that's done. This is only how the spectrum is drawn. Now comes what is the bandwidth of AM. Bandwidth means the range of frequencies. As you can easily see that the whole AM gets covered up from here, or you can say from here to here. Alright. So this range you have to just calculate. So simply the formula will be the highest frequency minus lowest frequency, that is Fc plus Fm minus of Fc minus Fm, and it will give you 2Fm. So the bandwidth formula of AM is 2Fm. And we all know FM is the frequency of message signal. Message signal is a low frequency signal. That means FM is going to be low, and therefore the bandwidth of AM is quite low. Alright. Now comes another thing, that is the power of AM wave. That means how much power is required to transmit an AM wave. So how do we calculate it? Simply, first of all, let's write down the expression for the whole AM wave. The first term, that is the carrier signal, the second term, that is the upper sideband, and the third term, that is the lower sideband. So how to calculate the power? See, I will show you in rough so that you can understand at once. Power formula is simply V squared by R, where V is the voltage, or you can say here in the case of signal, volt unit is for amplitude. So here V is the amplitude. Not only the amplitude, in fact the RMS value of this amplitude. So what is the RMS value if we have to take over here? It would have been root V divided by root 2. And when you will square it, divided by R. R is the resistance. So here the resistance will be taken to be 1 ohm and simply power will be given by amplitude square divided by 2. Is it clear to everyone? I hope I am clear. So it is V square by 2. So simply what you have to do, if you are asked to calculate the amplitude or if we are going to calculate the power of carrier, we simply have to pick up the amplitude of the carrier, square it and divide it by 2. So the power of carrier is EC square by 2. The power of upper sideband is just pick up the amplitude, square it, divide by 2. And similar will be the power for lower sideband. Just pick up the amplitude, square it and divide by 2. So it will come out to be EC square by 2. It will come out to be MEC whole square by 8 plus MEC whole square by 8. Alright. So total power is this. Total power is this. Alright. Now if we add them, it will give you MEC whole square by 4. I have added the powers of upper sideband and lower sideband. This is power upper sideband, this is power lower sideband, this is power of carrier. Alright. And now here I am going to take EC square by 2 common and I will be left with 1 plus M square by 2. EC square by 2 is nothing but it is PC, that means power of the carrier. So the formula for total power reduces to power of the carrier multiplied by 1 plus M square by 2. This is the total power. This formula has to be also remembered, plus the concept that from where I have started calculating the power of the whole AM wave, this concept should be also remembered. Alright? Because whenever the numerical does not come directly, so that concept will be used. I'm sorry. So let's see the numericals on this particular formula. So now you are given a numerical here. Here if you read this numerical, you will find that the power of carrier has been given. Modulation depth has been given. 60% means it is 0.6. And you are asked to calculate the total power. So you will simply apply the formula first and then you will put the values and calculate your answer. Your answer will come in watts. So the answer for here will be 542.8 watts. So this is how we calculate it. Now we have another variety of numerical here. Here, just read down this numerical. We have a 320 watt carrier which is simultaneously modulated by 2 audio waves where modulation percentage is given 45 and 60 respectively, and we are asked to calculate the sideband power, total sideband power. So here you can't use the formula directly because the sideband power has been asked. So you just need to recall from where we started calculating the power. The total power was power of the carrier plus power of the upper sideband plus power of the lower sideband. Yes, and the total power is power of the sidebands. That means PUSB plus power of lower sideband will give you total sideband power, and this is what has been asked. Alright, but you have been given two modulation percentages over here. So first of all, power sideband is total power minus the power of the carrier. You have the carrier power but you don't have the total power. So you need to calculate the total power. So for the first case, first of all, when the modulation percentage is 45%, that means M is 0.45, we will calculate the total power, which will be PC, that means 320 multiplied by 1 plus M square by 2, that is this. And from here, whenever you will calculate it, you will get the answer as 352.4 watt. Alright. And by applying the power sideband formula, that is total power 352.4 minus power of the carrier, you will get 32.4 watt. So for the first case, you calculated the sideband power. Now for case 2, when the M percentage is 60%, that means m is 0.6, you will again calculate the total power by applying the same formula, and you will get the answer as 377.6 watt. Again you will calculate the sideband power and you will get total power minus power of the carrier, which will give you 57.6 watt. Alright, now the total sideband power which can be calculated is 32.4 plus 57.6, which will give you 90 watt. Alright, so this is 90 watt. So this is how we calculate when the numericals are not given directly. Now comes again another variety of numerical, that is antenna current has been given of an AM transmitter, that is 8 amperes, and when it is the current value when only the carrier is sent, but it increases to 8.93 ampere when the carrier is modulated. So here the values are given in the form of current, but we haven't learnt any formula in the form of current. We have learnt in the form of power. So how to change it, that form, into the form of current? This is how we all know that we have learnt this formula. So in order to convert it in the form of current, what we can do, we can apply the formula of power in the form of current. So it is I square R. So total current square into R and carrier current square into R into 1 plus n square by 2. R is 1 ohm, or you can simply cancel out. So you will be left with IT square is equals to IC square 1 plus n square by 2. Alright. Now total current is given, that means after modulation, that is 8.93. Carrier current is given, that means 8 ampere when it was without modulation, and you are asked to calculate M. So from here you can calculate M. That will come out to be approximately 0.7 or 70%. Alright. Now in the second part of the question, you are asked to calculate the antenna current when the percentage M changes to 0.8. That means here M is given to you. You have to calculate the total current, and the carrier current is going to remain the same, that is 8 ampere. So you can put all the values in the same formula of current and you can find out the value. You will get the current value of the second part as 9.12 ampere. So just verify your answers, and I have made these questions solved in my separate videos as well, whose whose links are already given in the description box. Please refer to them. Now another variety of numerical is here. Just read down the numerical. Here an oscillator of a simple AM transmitter where a 50 microhenry coil has been employed and 1 nanofarad capacitor has also been employed, and the audio frequencies are given up to 10 kilohertz. You are asked to calculate the frequency range which are occupied by the sidebands. So here in this particular case, frequency range has been asked for the sidebands. That means you are asked to calculate upper sideband frequency and lower sideband frequency, and for this you must have the formula with you. Now you just need to identify what is FC and what is FM. If we have these values, we will be able to calculate both the frequencies. Now here a value of L is given and C is given. We all will remember, 1 nanofarad. We all will remember that in 12th class we have gone through an LC oscillator topic where the frequency of the LC oscillator is given as 1 upon 2 pi under root LC. Alright, and it has been told in this question that this output of this oscillator is modulated. That means this is the frequency of the carrier, and the signal which is going to modulate your signal, it is audio frequencies, that means FM, which is 10 kilohertz. So you can calculate FC from this formula, that is 1 upon 2 pi under root LC. FM is already given. Just apply the formulas for the frequencies of upper sideband and lower sideband and you will get the answer. So you will get the answers as, for the upper sideband it will be 722 kilohertz approximately, and for the lower sideband it will be approximately 702 kilohertz. Alright, so this is how we calculate. Now we have another variety of numerical here, that is the percentage saving has to be calculated when the carrier and one of the sidebands are suppressed. See, in the total AM signal, when we find out the expression for the AM signal, we had three terms over there. One was carrier, another was upper sideband, another was lower sideband. So let's write them. So these were the three terms. Alright. So now as you can read in the question that the carrier and one of the sidebands are suppressed. Suppressed means they have not been sent, meaning their power has been saved. So one carrier and one of the sideband power has been suppressed. So what was the power of carrier? EC square by 2, and the power of upper sideband or any of the sidebands, because the amplitudes were same, so power was also same, it was MEC square by 8. So these two powers are suppressed. Alright. So how to calculate the saving, percentage saving? It is simply power saved. And how we have saved the power? By suppressing carrier and one of the sidebands upon total power into 100. So whenever you will calculate the power saved, it will give you EC square by 2 common you can take, and it will, you are left with 1 plus m square by 4. So power saved will be PC 1 plus m square by 4, and the formula for total power is PC 1 plus m square by 2 into 100. PC will get cancelled out. You are left with the formula 1 plus m square by 4 plus 1 plus upon 1 plus m square by 2 into 100. So this is the formula which we have derived from the percentage saving. Alright. So now you can put the values of m's over here, different m's over here, and you can calculate the percentage saving. Now you can put the values of m's over here for the first and the second part, and just mention the answers for both the cases in the comment box. I'll tell you whether they are right or wrong. Alright. So now another question, variety of question we have, where a modulating signal has been given, that is 10 sine 2 pi into 10 raised to the power 3 t. It has been a sinusoidal signal where this 10 represents the amplitude, unit is volt, and omega t. So this whole is omega, and if you are going to calculate the frequency, you will divide it by 2 pi. Similarly, carrier signal, amplitude is given, sine omega t is given, and you are asked to calculate different values. So the only thing to understand in this particular question is that you must know how to recognize which signal is message signal and which is carrier signal, which has been already given clearly in the question, and you must be able to correspond it with the expression. Like message signal is 10 sine 2 pi into 10 raised to the power 3t. So you must know that this is the amplitude, that is EM equals to 10 volt, and FM equals to omega divided by 2 pi, that is 10 raised to the power 3 hertz. Similarly, carrier signal is 20 sine 2 pi into 10 raised to the power 4t. That means EC, amplitude of carrier, is 20 volt, and FC, that is the frequency of carrier, is 10 raised to the power 4 hertz, or you can say 1 kilohertz. Now you will be able to calculate all the values very easily. First of all, M has been asked, which is EC by EM, which is EM by EC. So you can calculate it. Percentage modulation, simply multiply it by 100, modulation index. Frequencies of sideband components, that is upper sideband and lower sideband frequencies. Formula is this. Amplitudes has been asked, so amplitude of upper sideband and lower sidebands are same, and the formula is MEC by 2. Okay, and bandwidth has been asked, formula is 2FM. Alright, so just calculate your answers and draw the spectrum, and please tell me in the comment box what answers you all have got. So that was the numericals on different types of numericals on AM. So I hope we have covered a huge variety of numericals over here. Now let's come to the concept of modulation index. See, modulation, depending upon this value of modulation index, whether it is less than 1, greater than 1, or equal to 1, we have three types of modulation. So the waveform that I have shown you earlier, here was the AM signal with respect to time, and I have shown you that the envelope does not cross the axis. That means the above envelope remains above the x-axis. It does not crisscross the axis. So this type of modulation, when we receive such type of AM signal, in that particular case modulation index is less than 1 and it is called linear modulation. When we receive an AM signal in this way, when the envelope just touches the axis, alright, so here the modulation index is 1 and this is called critical modulation. But when we receive an amplitude modulated signal like this, where the envelope crosses the axis, here we have distortion in the signal, and for this particular case M is always greater than 1 and it is called overmodulation. So what is recommended is M less than 1 is always recommended. Alright, that means linear modulation is recommended. That means M should be always less than 1 so that distortion can be avoided in the modulated signal. So that was about the modulation index. Now we have advantages of AM wave. See, whenever we talk about the advantages, simply we should mention that the transmitters and receivers are simple, they are cost efficient. We all know that after modulation that waves can travel long distances, and the bandwidth occupied by AM wave is very low because the formula is 2FM, where FM is a low frequency. Alright, now we have disadvantages. Here power wastage takes place. How? If you pay attention to the expression of AM signal, so in that particular case, you will find that we have three terms: carrier, upper sideband and lower sideband. Carrier is simply a carrier. You cannot see in that particular term that any message is hidden. See, let's go back to the expression of AM signal. Okay, I'll stop here. See, in the expression of AM signal, we see that we have three terms. The first term is a carrier and it is simply a carrier. It does not have any message attribute in it. Alright, so it is empty carrier. Alright, so it means the power wastage takes place because we are not transmitting any message in this particular term. In the other two terms, as you can see, the amplitude of both the terms are same. upper sideband and lower sideband. That means the same information is being transmitted through both the sidebands. Alright. So we can even avoid one of the sidebands. So here power wastage takes place in this particular form, that the carrier, we are transmitting a carrier signal which is not required because we are not transmitting any information through this first term, and we are duplicating the information in the other two terms. So therefore we are saying that here power wastage takes place. Also, the noise factor affects the amplitude very much rather than frequency. Noise affects the amplitude more. Therefore, this is a disadvantage of AM wave. This is a disadvantage of AM wave because in AM wave, the amplitude gets easily affected by noise. So this is also one of the disadvantage of AM wave. Alright. Now let's come to the modulation of AM wave. That means how we have to make the circuit in order to generate the AM wave. So in this particular case, we are using a square law modulator where we are using a square law device. See, every square law device has a function. I'll show you the function, but first of all, let's see the block diagram carefully. Here we have put a summer first of all, where we are adding a message and the carrier. Alright, then whatever output we will receive, we are going to feed it in a square law device, which is a non-linear device, and the output of the non-linear device will be fed into a filter. Now just remember what is your objective in AM. Your objective in AM is to receive three terms in the expression, that is the carrier and the two sidebands. So sidebands will be only received when you have a filter which can transmit a frequency of FC plus FM and FC minus FM. So here you need to use band pass filter because it was going to transmit a particular band. If you are going to tune it to a frequency FC, then it will be able to pass some frequencies above FC and some frequencies below FC, that is FC plus FM and FC minus FM. So therefore we are using band pass filter over here. So let's see the calculation fast. I have written V1t, it is MT plus EC cos omega CT. Then the output of square law device is given by this expression. We have to remember this, and it is a non-linear expression. Just put the values, keep on calculating. Wherever you get a term of cos square x, just replace it by 1 plus cos 2x by 2, so that we can easily able to figure out that which terms will be passed through filter and which terms will not be passed through filter. Alright, finally we will receive a term. We will receive the terms, and as our band pass filter is tuned to omega c, so it's going to pass. See, the function of band pass filter will be like this. If it is tuned to FC, it will pass FC, it will pass FC plus FM, and it will pass FC minus FM. So all the components which are having these three frequencies will be passed. So as you can see in the expression of V2T, the frequency is omega m will not be passed. Omega c will be passed, second term. Here the frequency is 0, it will not be passed. Third term has 2 omega m, it will not be passed. Fifth term has 0 frequency, it will not be passed. Another has 2 omega c, it will not be passed. And the last two terms have FC plus FM and FC minus FM. So these three terms will be passed, and that is what we needed. This is the expression of our AM wave. So this is how we receive the expression of AM wave. In order to see it in detail, you can separately go to the video of modulation techniques of AM and refer that video. The link is given in the description box. Now comes demodulation of AM wave. See again, detector. Detector is also alternatively called demodulator. So here we are using two demodulators. One is square law demodulator, another one is envelope detector. So simply now in this demodulation case, we are having the input in the form of AM wave. Alright, we will feed it directly to the square law device, the expression of which is already known to us. But here the filter that we will place will be low pass filter, because here our objective is to demodulate. That means separate the carrier and the message signal and take our message out. Alright, so here we are only concerned with getting our message signal. So we need only one frequency component at the output side. Therefore, we are going to use it low pass filter, because low pass filter means it will give you a signal having value 0 to omega m, because we have tuned it to omega m. Alright, so here again we have this VIT is AM wave. AM wave is nothing but the expression. If you see the derivation, please pay attention to the derivation. We started the derivation from here, where we replaced A into the expression of EAM wave. So as you will look to the derivation above, this was our A that we calculated, and the whole expression was A cos omega ct. We will reduce this expression for our convenience to 1 plus m into cos omega ct. M here will represent our message. I'm sorry. So wherever this m will come, we will by default take it that cos omega mt is also attached with it. Then we took VIT as this expression. So our VIT is this. Now we started calculating V naught T. V naught T expression is this. It is the output of square law device. We put the values, we kept on calculating, and when we replaced all the cos square x values by 1 plus cos 2x by 2 values, and then we deployed a low pass filter to it, and we found out that we only can pass two frequencies here, that is 0 to omega m, that is 0 and omega m. So these two components were having 0 frequency, and this was having omega m because m is here. Alright, here also there is m, but when it becomes square, that means our message has been altered, thus its square has been taken, so that is not message, in fact that is distortion. Alright, this is DC term. So we will put a filter and we will filter these two terms, and we will take only this desired signal out. So this is the message signal. So this is how we demodulate by using square law demodulator. Another type of demodulator that we have, that is envelope detector. Envelope detector is a very simple circuit where we have a diode, we have a capacitor and resistor which are connected as it is. Now let's draw the input waveform. Input is nothing but the AM signal, as we all know. This is the AM signal which is fed as input to the envelope detector. See, there is a very simple concept. Just look at the waveform. First of all, the positive half cycle will come. That means this. I'll show by highlighter. This positive waveform will come. So when this positive waveform will come, we will have a plus and a minus here, and the diode will be forward biased, due to which the capacitor will charge up to the peak value. So the capacitor gets charged and we record this value. So capacitor gets charged up to this peak value. Alright. Now in the second half, this negative half cycle comes into light. Please see the yellow highlighter, and the signs get reversed and our diode gets reverse biased. Okay, so our capacitor starts discharging, but the discharging speed is slow as compared to the charging speed. So the only discharge has reached up to this point. And in the meanwhile, again the positive half cycle comes. Again the diode gets forward biased and the capacitor charges up to the peak value. Again the negative half cycle comes and the capacitor starts discharging. Again the same process repeats, and in every positive half cycle we record the peak charging value of capacitor, which gives us these points. When you will join these points, you will get a rough envelope of your message signal. So envelope detector is not a very accurate signal. In fact, it gives an approximation of the message signal. So wherever the accuracy or the clarity is not required, we can use envelope detector, because when we will join these points, we will be getting an envelope. So wherever the accuracy is not required much, we can use a very economic way of demodulating an AM signal, that is envelope detector. So this is how we demodulate AM detectors by the two technologies. So I hope that this video will help you in your exams or during your understanding or revising the topics. So all the best for your exams, or all the best for your learning. Goodbye.